Okay, so now we're going to continue to work on chapter 9. Now, this is 9.7, where we are introduced to the Taylor series polynomial. Now, keep in mind, as I mentioned earlier, because of the fact that we're so close to the end of this course, you will not actually have to do any assignments based on this material or anything that comes after it. And it's not going to be in your final exam, but it's awfully important material. So I want to make sure that we have had some exposure to it because you'll probably need it again in Calc 2. I'm sorry, Calc 2, Calc 3, and anything else that follows along. So I would recommend that you just at least watch the video and, try to absorb as much as possible, but you do not have any assignments including the final exam that will be based on this material. So it's just for the fun of it, okay? But yes, it is awfully important. That's why I want to make sure that we finish this before the course ends. So especially this first topic, the Taylor series approximation, it's an awfully useful tool to help us come up with reasonable approximations to functions that we're working with, especially when the functional form itself is not really known. So we'll start here with 9.7. And we're going to see both Taylor and Maclaurin polynomial approximations of elementary functions. And so we start by noting that what we're trying to accomplish, as you can see in this graph, is to take a function of some kind and approximate it as best as we can. And in this case, as you can see, we've got a function p. Actually, the function is f that we're trying to approximate. The p is the polynomial that we are creating to approximate it. So the f is the actual function. And so the straight line, which is being labeled p of c, is the approximation. Now, if you notice, what we're really interested in is the approximation at a specific point. And so in this case, that would be the point C, f of c. So what we would like to be able to do is come up with a functional form that gives us the correct value of the original function, f of c, at that point on the approximation, which is p of c. Okay, so here, this is f of x. This is p of x. We want to approximate f of c with p of c. And I can see from the graph, I mean, at that point, the two look like they're awfully close to each other. It appears that this is a very good approximation, but only at that point. As we get further and further away from that point, the two functions are actually not very close to each other at all. But our main focus is right here. Now, it turns out there's quite a few different ways we could do this. So what we're going to do is require that whatever this p of c function is, it's going to satisfy two requirements. Number one, p of c has to equal f of c. And the first derivatives also have to be the same. In other words, at that point, the two curves touch and the slopes are the same. That's the least we could do. If we don't impose both of those conditions, we could have a lot of very strange results. So it has to be at least those two. It could be more, but for now, we'll start with this. All right, so how do we do this? All right, so we'll start with f of x equals e to the x power. And they're telling us that they want us to find as an approximation of first degree polynomial, which simply means a linear function, which is written like this. Okay, so let's see how that works. Now, of course, e to the x looks like this. cuts through the vertical axis at the point 0, 1. And then after that, it grows fairly quickly. At first, it grows very slowly. Then, after we get into the first quadrant, it starts to grow very quickly. And so, what we're looking for is a linear approximation to this function at a specific point. Okay, what point would that be? That would be the point 0, it looks like. Okay, so f of x equals e to the x power. And we want a function which we're going to call p of x, which is our approximating polynomial, equals, actually, you notice the subscript 1 there to remind us that this is meant to be a first order or first degree polynomial, which is a linear function. We're going to call it a0 plus a1x. Of course, a0 is the intercept, and it is the slope. All right, well, how do we do this? All right, well, also keep in mind that we're trying to do this at the point x equals 0. So the first thing we need to do is take the derivative of this function, because remember, the two things we're lining up are here. We need both of these to match. So all right, so we know that f of c is e to the c. Actually, let's do it this way. Let's just write it as f of x. Then we can find the c later on. Okay, so those are both, of course, equal to each other. And c, the point that we're looking for, is 0. Right? So then we know that f of 0 is 1. And then f prime of c, or f prime of 0, is also, of course, 1. Great. So therefore, in order to find the coefficients of our polynomial, we have to show that first these are equal, and then secondly, these are equal. All right, so P1 of 0, here it is up here. Let's move this down here. P1 of x equals a0 plus a1x. So of course that means that P1 of 0 is a0 plus a1 0 equals a0. And in order to see if these are true, or this is true, we have to set this equal to 1. Okay, so in other words, we just got through showing up here that f of 0 was 1. So in order for this condition to hold, it must be true that a0 equals 1. All right, so we got our first coefficient. Now for the derivative, so let's see, I don't think we took the derivative of p of x yet. No, we did not. All right, so let's do that right now. Okay, and so that means that since p prime 1 of 0 equals f prime of 0, that indicates that, by the way, since this is a constant, this is just a1 anyway. And so that means that both a0 and a1 equal 1. So our polynomial approximation is simply going to be 1 plus x. Okay? Now, the constant that we're using here, the c, is sometimes called the center. So if you go back to this graph, and let me just see if I can draw it a little better. The polynomial that we just estimated is 1 plus x, and that's going to be right about here. So again, at that point, f of 0 equals p of 0, and f prime of 0 equals p prime of 0. So that is our first case of approximating a nonlinear function, in this case with a linear function, in such a way that the two agree at that one point that we're interested in, with both the point itself and the slope. Okay. Now we could have also insisted that we have more matches. For example, we could have insisted that we line up the two second derivatives and the third, but we're not going to do that here. Okay. For some complicated functions, that may become necessary, but here we're only interested in the first two derivatives. Well, actually, not the first derivatives. F of x equals p of x, and f prime of x equals p prime of x. So this gives us kind of an idea of what all of this chapter is all about. And here you've got their copy. This is, of course, a better picture than mine, but you get the idea. Okay, now in general, what are we doing here? This polynomial, you'll see here, shows us an nth degree polynomial, but normally an nth degree polynomial looks like this. All right, so using their notation, it would be this. Pn of x would be, first we'd have a constant, which we'll call a0, a1x, then we would have a2x squared, and we'd have all the way up to n, whatever n is. But here, what they're doing is they're extending this a little bit. What they would like us to do is see that if we're going to expand this polynomial about a specific constant c, then we can write it like this. Now, you notice what's happened here. In each case, x has had c subtracted from it. So that means that the functional form looks like this now. Okay, so the first term is not affected. So here, all the x's are being replaced with x minus c. And then we go all the way out to the end. Okay. And that's what the Taylor series is going to look like, by the way. We're working up towards the Taylor and the Maclaurin series. The Maclaurin series differs from the Taylor series in that with the Maclaurin series, the center is always 0. The Taylor series can have any center. But we need to do a couple more things here. These actual coefficients, a0, a1, a2, we need some kind of a functional form for each one. So what they've done here is they've shown you that if we keep differentiating this polynomial enough times, we could show that the final result would look like this right here. So this is the nth Taylor polynomial, or the nth order or nth degree Taylor polynomial centered at C. Okay, and again, that's based on all the the derivatives that we took. And so this is what we're actually going to use for our problems. And you can see that we've replaced the a's with the actual derivatives taken from the original polynomial. Okay, so this is our Taylor It's sometimes it's called a Taylor polynomial. It has a few equivalent names. Some books call it a Taylor expansion. Some call it a Taylor um, series approximation. There's a lot of names. As long as the word Taylor is in there somewhere, you know that they're talking about this setup. And so C is the center. And if the center, of course, is zero, then you would just end up all those C's would just go to zero. So this is a very general expression. We can literally expand any function around a specific point with a polynomial. Okay, even functions that are not even close to being polynomials themselves. Okay, so in other words, we can apply this literally to any function we can think of. And the beauty of the setup is that the more accuracy we need, the more terms we use. Okay, so in other words, we can have as many of these terms as we want. Up here, we used a linear function, and that might have been good enough. But if we need a quadratic function, sorry, then we just add one more term. So in other words, you would add this term if you need a quadratic function, and then you would keep going if you need a cubic function, et cetera, et cetera. So you can choose as many terms as you want with the understanding that the approximation will continue to improve. But at some point, it starts to become overkill because you're adding um, terms that have smaller and smaller values. And so there comes a point where you want to cut it off and decide this number of terms is quite sufficient for what I'm trying to do. So, you don't have to have a huge number of terms to come up with a good approximation in many cases. Now, this is the equivalent Maclaurin series. And if you notice, the only real difference is that it's centered at zero. Okay. So this is Taylor up here. This is Maclaurin. Make sure I'm spelling that right. It's Maclaurin. Okay. Uh, I think that spelling means that it's Scottish. Okay. Now, by the way, the problems would tell you if you're supposed to use a Taylor series or a Maclaurin. Okay, it has to be specified in the problem if you're working on one. So here, what they want you to see is if we used a Maclaurin polynomial where f of x equals e to the x, that implies, of course, that because it's Maclaurin, that the center is zero. So you can see here's the formula. Let's use this. And they want us to, they're going to show us several of the key terms. So that means that, let's say, P of 2 would be all right. So we need to know f of 0. Now, luckily for us, they chose this function very carefully because if you notice, the derivatives are all e to the x. Okay, that really does help. So by making all those substitutions, you'll see that P2 of x. Okay, hold on a second. Um, 1 plus, now f prime of 0, as you can see, is 1 times x. And then f double prime of 0 is 1, but that's divided by 2 factorial, which is just 2. So you can simplify this as 1 plus x plus 1/2 x squared. Now, if you notice, just a little while ago, when we were trying to approximate e to the x, without us being aware of it, what we were actually doing, because they chose to expand it at 0, we didn't know at the time that what we were actually doing was creating a Maclaurin polynomial of degree 1. Okay, so in other words, P1 is 1 plus x, and that's what we found earlier. But if we need more accuracy, we can add a second degree, and we end up with 1 plus x plus 1/2 x squared. Okay, and if you need more accuracy, you just keep adding. You can go out as far as you need. But in practice, many applications don't require more than a couple of terms here. So, but then in principle, you could define as many of these as you want. All right. Now, here, they're going to have us do a Taylor polynomial, the first 4 of them, when f of x is log x, and the center is 1. Okay. And again, they want p 0 through 4. And so let's go get the formula again, because we clearly don't have it memorized just yet. Let's see. And they also tell us that the function is log x. Of course, we need to know that. And the center is 1. All right. So we have f of x is log x. F of 1 is log 1, which is 0. F prime of x is 1 over x. Okay, so we'll need the first 4. Okay, f, the third derivative is going to be and then finally f, the fourth derivative. And so those are the constants that we're going to need. All right, great. All right, so then now P0 would be just this FC, but of course, remember that C is equal to 1. And so we're going to wind up with 0. So we already figured that out. It's 0. Okay. And let's see, let's double check these. 0, 1, negative 1. Uh-oh, what happened? Oh, what did I do? Oh, I'm sorry. This is negative 1. All right. All right, that's better. 1, negative 1, 2, negative 6. All right, that's all we need. E1 would be these two. Or in other words, now remember, C is 1. F prime of, actually, all right, I'll just fill in the C's right now, and then we'll get back to this in a second. F of 1 is 0. F prime of 1 is 1. Okay, great. So we start with 0 and x minus 1, and then P2 is, actually, I'm going to copy this again so I don't have to keep scrolling back and forth 100 times. So we're going to have F of 1 plus F prime of 1 times x minus 1 plus F double prime of 1 over 2 factorial, or 2 x minus 1 squared. All right, now let's go find those numbers and copy them. So f of 1, as we saw earlier, is 0. F prime of 1 is 1. F double prime of 1 is negative 1. Oh, but we have the 2 there. Let's not forget about that 2. And then we have x minus 1 squared. Okay, so in other words, we get the first two terms we already had, plus we have another new one. So we have the x minus 1 minus 1/2 x minus 1 squared. That is what we mean by P2 of x. Okay. Now they may have written it slightly differently. X, no, that's exactly what they have. And then we still need P3 based on this formula. So we just add another term. Now, of course, they've got, they didn't show all the intermediate terms. They've got all these dots here. So let's do this first. So that's the pattern that's forming here. So those are the terms we need now for P3. And so then keeping in mind that 1 is C, you have f of 1 plus f prime of 1, x minus 1, f double prime of 1 over 2. Now 3 factorial is 6, so this one becomes f triple prime of 1 over 6, x minus 1 cubed. So this one is getting kind of messy here. So we can certainly do this if we need all this accuracy. If we don't, you can see that it could be overkill. So we're going to have 0 plus 1. So again, this replicates what we just did a few minutes ago. then we had um, there's no point in recalculating these. It's minus 1/2 x minus 1 squared. It's the new term that we have to watch out for. So what is that equal to? We have um, f to f, the third derivative of f evaluated at 1, which is 2, 2, 6, which is 1/3. All right. So that would be the last term. And so this is our third order polynomial. You can see it's getting very, very messy. So it's the same one, except at the end we have 1/3 x minus 1 cubed, and then finally p4 of x. So based on the formula, again, that we've been using, it's going to be f of c plus f prime of c, x minus c, f double prime of c for 2 factorial, x minus c squared plus f triple prime of c. Let's see. And then finally, the fourth derivative. All right, so the first part is exactly the same. So we'll just fill those back in as the previous one, I mean. P3 of x was this. So we'll just copy that. We'll have 0 plus 1, x minus 1, plus minus a half, x minus 1 squared, plus a third, x minus 1 cubed. Now it's the last piece that's missing, and that's going to be the fourth derivative evaluated at 1, which is from up here, -6, okay? So we're going to have -6 over 6, so it's actually minus 1. Actually, I'm sorry, that we already have that one. It's here it is, -6 right there. No, that one. This last term, the fourth derivative of evaluated c is -6. 4 factorial is 24. So this ratio is -1/4 x minus 1 to the 4. Now, by the way, when you see enough of these, you start to realize there's a pattern here. All those calculations were fine as far as they go, but if you notice, what keeps happening is the coefficient is 1 over x. Then we have x minus 1 to the x power. Okay, so in other words, if there was another term, it would have been plus 1 over 5, x minus 1 to the 5th. And then the next one would have been negative 1 over 6, x minus 1 to the 6th. So there's a very noticeable pattern here. We're so busy filling in all the details that eventually you want to stop and see if maybe there's some kind of pattern that will help us understand what we're doing. So that way you don't, have to go nuts and, keep filling in all these terms. It should be clear what's coming next. All right, let's see what they mean for us to do. Now, here what they're trying to do is show us the graphs of f compared with P1 and P2 and P3 and P4. And so you can see, the more terms you have in your polynomial, the closer the approximation will be. But you have to ask yourself at some point, when is enough enough? How accurate do you need to be? And that's really what's going to determine how many terms you're going to use. Now, here's another one that involves sines and cosines. Now, this one is a little different because of course, the derivatives alternate back and forth. with sine and between sine and cosine, but also negative and positive. Now here they're specifically asking for a Maclaurin polynomial, which means that the center is zero. Okay, this was a Taylor polynomial, which could have any center. But I noticed for some strange reason, they're only asking for 0, 2, 4, and 6. So, yeah, I mean, we don't have to go through all this again, but you can see that we eventually end up with this. Okay, so if you have a sixth order Maclaurin series, this is what it will look like. And they're letting us know that um, it's awfully accurate. Okay, in other words, if you're going to have a sixth derivative in there somewhere, you're going to get awfully close to the correct value. And they're showing us the graphs of the two, so you can see visually that they do look very similar. Now, of course, when we do one of these polynomials, what we're doing is creating an approximation. There's always going to be an error involved. And so the error itself is called a remainder, which you might remember from when you learn long division. If you've got two numbers that are not, one is not evenly divisible by the other, there will always be a remainder. So here you can see that the exact function can be written as an nth degree polynomial, Taylor polynomial, plus some kind of remainder. And so it's a remainder that we're trying to minimize. And so then they're saying that algebraically, this implies that Rn, the remainder, is simply the original function minus the polynomial, and the absolute value of that error term is called the error. Okay. Now there's all kinds of theorems about how large this error can be, which is important if you, let's say there's some number that you need this approximation to be within a certain tolerance of the correct value, and you're not sure how many terms to use in your polynomial. Now you can go ahead and try them all. You can try the first and the second and the third and the fourth, etc. But this gives you an opportunity to find out how large your error it might be with a given order polynomial. And that way you can solve in advance for how many terms you think you'll need to come up with an approximation. So there's a general formula for this remainder. And so what they would like us to do is try this example with the remainder. So here's our third order Maclaurin polynomial. So they're assuming that we've already taken care of this. And oops. Yes, let's copy this in here. So they want us to solve for sine 0.1. With this third order Maclaurin polynomial evaluated at x equals 0.1. So we're going to solve for P3 of 0.1. And what is that going to give us? Well, they've got the original, this P3, and they've also given us a general formula for the remainder. So the third, when we approximate with the third order polynomial, the remainder will require the fourth derivative, which you can see here. But the z there is a constant which is bounded between 0, because that's the center, of Maclaurin polynomial and 0.1 because that's the value that we're using for this function. Okay, so z is some number between 0 and 0.1. And so because of that, um, you're going to have to start by actually calculating the function itself. In other words, sine of x evaluated at 0.1, which is what we're interested in the first place. Yeah, it says it right there. We're trying to find 0.1. So sine of 0.1 using this formula is going to be 0.1 minus 0.1 cubed over 3 factorial, which is, of course, 6. So you take out your calculator. Hold on 1 second. Let's see what this is equal to, approximately. Now, I'm not sure how many digits they need, but 0.1 cubed divided by 6 is subtracted from 0.1. It's a, according to this, oh, I know what I goofed, sorry, 0.1 cubed. All right, hold on 1 second. Point 0.0998. All right, that's probably good enough. Using the, actually, you know what I just realized? We're supposed to use the approximation symbol here because this is not exactly correct. What I've done here is I didn't put sine 0.1 in my calculator. I used this third order Maclaurin polynomial to come up with that. So it's approximately 0.099833. All right, fine. Now, because the fourth derivative of z is sine of z. Now remember, the original function was sine of x. Um, hold on. Okay. So therefore, the error in absolute terms has a boundary of, first it must be positive. Now remember, R3 is the remainder of this function evaluated at 0.1 using a Maclaurin series. We know that the formula tells us that this is going to be f to the fourth derivative of z over 4 factorial times x to the fourth. So let me make a note of that on the side so you can see where this is coming from. R3 of x equals f4. By the way, some calculus books use Roman numerals for these very high order derivatives. I just noticed that they're not doing that. I've been using the little Roman 1 IV. Just be aware that I mean the fourth derivative here. Okay, great. So therefore, now remember the fourth derivative is simply the sine of x. So to do this at 0.1, Okay. And they're helpfully showing us that it's approximately point, what is that? Five zeros. One, two, three, four, five zeros followed by a four. Approximately five zeros followed by a four. So what they're telling us is that as a result of all this, because that's the remainder, that we can make the following statement. Um, that the correct value is somewhere between. Now remember, originally we simply plugged 0.1 into this polynomial and we got 0.099833. 0.9983. So they're telling us that the actual value of the sine is somewhere between the same number plus R3, which of course is, as we just saw, 0.00004. And so when you add those two together, you get 0.099837. So think of this as the lower and upper limit of our approximation to sine 0.1. Now, if you want to know the exact value, of course, you pop it into your calculator. So let's do that right now. 0.099833.4. Right. Okay. No, that's good. That works. This is definitely in between the two endpoints. So that's the actual value, and this range represents the range of possible values for sine 0.1. So in other words, using this approach, we can not only come up with a good approximation, but we can also estimate or establish an upper limit on how much error is involved, which is kind of nice because we understand how this was constructed. We can figure out what is the maximum issue or problem we can have or difference compared to the actual number. All right, now, what do they want us to do? We're going to do a first degree polynomial for this function. Using the same techniques we had up here. So let's go copy that of what we had earlier. T1 they want, it looks like T1 is, well, actually, we don't need to do all that. This is, it doesn't specifically say, in fact, it says use x equals 2, which means we have to use a Taylor approximation. Which means it's going to be a constant and some function of x. So for P1, we only want these two terms. Okay. And we're being told that the function is 4 over radical x. And the center is 27. All right, so we only need one derivative. Let me see if I can streamline this a little bit. I'm going to rewrite this a little bit, make it a little simpler. Great. So we need to know f of 27. All right. So what is that equal to? It's approximately 0.7698. The derivative over here, all right, let's see what that is. Oh, whoops. Okay, hold on. I made a dumb typo here. Negative 0.0142, let's say 56. That's close enough. So anyway, what do we need to know? E1 of x equals f of c, f prime of c, x minus c. F of 27 is 0.7698. F prime is negative 0.014256. All right. So what choices did they give us? Ooh, so I get what they did. Um, yeah, this one, it looks like they wrote that as something over 243. Probably that was a smart move compared to writing it like this. Mm. Well, all right. I'm going to leave it like this for now. We know that it's x minus 27. So they got 4/3 for f of c. Now, wait a minute. I don't see that. Based on this polynomial, the first term is f of c, which is 27. So if you take 4 divided by the square root of 27, that is no way 4/3. I don't know what happened here. There's something not right with this question, so let's just go on to the next one. Yeah, I mean, it's pretty straightforward. That's clearly not right. Yeah, I don't know how they got that. So for the Maclaurin series, we have this. We're looking for f of x equals e to the 9x. Now let's go back and get the formula for the Maclaurin polynomial. From way here is yeah, because it's understood when Maclaurin the center is 0, so it ends up being written like this. Okay. So they want P4. And the way this is written, we'll need f of 0, f prime of 0, x, f double prime of 0, x, sorry, over 2 factorial x squared. Okay. Now we just plug them in. And first we need the derivatives. Now, f prime of x because of the chain rule, this is 9e to the 9x. This is 81e to the 9x. And then the fourth derivative is whatever 9 times 729 is. Uh, 6561. So we need, let's copy that down here. F of 0 is going to be e to the 9, 0, e to the 0, which is just 1. Okay. Actually, we might as well solve for these before we go any further, because we're just going to be plugging them in. Oh, all right. Well, that'll be easy because you can see it's just the coefficient. Okay. Well, that was easy. So then we're going to have all right. So P4 of x equals 1 plus 9x plus 81 over 2x squared plus 729 over 6 x cubed. And then finally we'll have 61 over 24 x to the 4. All right. All right, so let's see what they offered us. Oh, it looks like it must be this one. 1 plus 9x plus 81x halves x squared plus 729 over But they've got a 4 there. What happened there? Did we do something wrong here? 3 factorial is 6. And then 2187. Wow. So they're claiming that it's A. So you know what must have happened? We have 1 plus 9x plus 81 halves x squared, 243 over 2. All right, so 729 over 6. If you divide that by 3, 729 divided by 3 is 243. All right, so that one's fine. And then the last one, 6561 over 24. Again, we're dividing by 3 to get, if 6561 divided by 3 is 2187. Yeah, we're good. Okay. It's the same thing. All right. They just reduced it a little more than we did. That's all. So this is the final answer. Okay. And you know, you can rule out like this one and this one because they have negatives. And then this one, the coefficient for x cubed is wrong. All right, so it's definitely A. Okay, great. Okay, so that is 9.7. Now what comes